Can you guess what that sound was? What about that one?
I'll give you a hint.
So these came in the mail.
I was curious to try one because there's a lot of people recommending this type of blade. These are sometimes called T-type blades because their profile looks like a T, but I believe they're actually P-type blades. P for parallel, T for tapered. Supposedly, they make parting off easier because of their concave top and wall clearance, which is all embedded in their geometry.
This particular one has 8% cobalt, so the tip should last a little longer than the plain HSS blades.
And if you remember, in the last video I mentioned how my straight blade liked to jump off of the tool holder. And that for harder materials, like stainless, I was much more successful using that thin blade. It's just less tool pressure during the cuts. That means I need a proper tool holder for that blade.
So why not make it suitable for both blades?
This is the only piece of stock I have big enough for the new tool holder. I'm pretty sure it's A36, cold rolled, and I'm aware it might not be the best choice in terms of wear resistance, but it might be just right to try out this different type of tool holder.
The first step is often squaring the stock. This is no exception, but I haven't had much success fly cutting this type of material.
I find A36 to be a bit gummy, and surface finish isn't always great. So I guess this time I'll try this massive face mill that was sent to me by mistake. I know this is too big for my mill, but how could I not try it? Especially after the arbor for my mill showing up at my door 2 weeks later, also by mistake. Yeah, she didn't bite either. But don't you worry. I'll be hiding behind 2 concrete walls feeding with a stick.
The surface finish is actually pretty good.
I'll finish squaring the stock using only one insert in the face mill. It's like having one big heavy fly cutter, and that mass really seems to make a difference. But when I'm about to finish, I realize the block is too big and will leave the tool overhanging a bit too much. But the block needs to have a certain width, so I take a few measurements and the most I can cut off is 10 mm. Milling that is an option, but that would be a waste of material. I think I'll try to make the cut in the bandsaw. Avoiding the vise pinching the blade is the tricky part here, so before that can happen, I'm sticking a shim in the slot and flipping the part. Then I can finish the cut until both parts are separated.
Next, I'll fly cut the last face, which is now rough from the bandsaw cut. Now it's time to cut the dovetail. This is the first time I'll be doing something like that, so I'm taking another holder as a reference. I don't want to overcomplicate this, but I want to get the dimension right. So I take a couple of end mills and rest their shanks against the angled faces.
That angle is 60 degrees.
Now I can use an adjustable parallel to take up the remaining space.
Back at the mill, I start by roughing a channel for the dovetail. Then, with the finishing end mill, that channel is taken to size. From that point, we can focus on cutting both sides of the dovetail. As I'm approaching the final dimension, I start to take measurements using a second adjustable parallel. This allows me to track the progress and keep the reference of the final dimension on the first. As soon as I can squeeze that between the end mills, I know I'm there.
Perfect.
Now we need to create some clearance for the solid tool post mount. And this is the perfect time to chamfer the edges on this face. Finally, some deburring and the dovetail is complete. The next feature is critical for the success of this tool, and that's how we'll hold the blade. I want to have it trapped in a way that it can't move in any direction, so I know I need to start with a slot. The question is, where's that gonna be? The short answer is anywhere, as long as the tip is right on center with the spindle axis. But the longer version requires a deeper analysis of the problem. First of all, I need that slot to be as low as possible in the tool holder. Then, I have two blades to support, the P-type and the straight one, and I'll be mostly parting steel. That means each blade should have some back rake, probably 5 to 7 degrees. For the straight one, that's easy, it's a matter of grinding that in the blade. In fact, that's already done. But the P-type is not meant to have the top ground, so that means we need to rest the blade on an angle. Now let's think about tool height. The straight blade will always have the tip in a lower position. That's because of the back rake grinding. That means the tool holder will have to go up.
Also, since the blade will be on an angle, stick out will matter, and the more retracted the blade is, the higher the tool holder needs to be adjusted.
So I think that with a straight blade on a 5-degree angle as retracted as possible, I can safely mark the location for the slot. And just to be on the safe side, I've given 2 mm of clearance to the top of the tool post. That's to make sure there's still full support if I need to move the tool holder up a little bit more. In theory, this blade position will support the two types of blades, with some room for adjustment at the top and a lot at the bottom. Now that we know where the slot's gonna be, we need to set up the part in the milling machine. The easiest way to make this slot on a 5-degree angle is to clamp the part directly to the table, using a square and an angle block to set the angle. But the indicator doesn't lie, and the table's front face isn't exactly square to the y-axis. Nothing a couple of taps in the right place can fix. There you go. I'm going to mill this down by 3 mm. That'll be enough to take the straight blade, which is only 1.5, and the P2, which is 3/32. That's roughly 2.4 mm. I did look for the 1/16 blade, which is a P1, but couldn't find any place online where shipping to me was available. That's why I'm still using the old blade. As for the height of the slot, I'm oversizing it on purpose. I need at least 1 extra millimeter that my slitting saw will take, maybe a little bit more. This 4 mm end mill creates extra clearance for the top of the P-type blade.
But while we're here, let's finish the slot.
Holding the blade. There's a couple of ways to make that happen, but remember when I said I wanted to clamp it so it couldn't move in any direction? This is it, and I might ruin this part right now. So here's the deal. I'm going to split these in two parts, the main body and the blade clamp. The clamp will be held by 4 screws that I need to tap as close as possible to the wall of the slot. That is, without breaking through. I think it'll be easier if I do it at this stage, so here it goes. Spot drill,
Tap drill, clearance drill for the counterbore, chamfer,
and tap M5. Next, let's cut this in the bandsaw. Fingers crossed it will make a straight cut. This might not be making much sense to you right now, but I'll explain in a few seconds. First, let's split the clamping part.
Oh boy.
That's gonna hurt. I think I need to make some arbors for my saws. And just like that, we have now two parts to address.
Starting with the clamp, I'm holding it in the vise in a 5-degree angle.
That way I can clean up the finish from the slitting saw cut. Then I clamp the part on each side with the help of the angle block and do the same to the bandsaw blade finish. One last dance and we bring back the dovetail cutter. Back on the main body, I clean up the new face from the split until the shortest blade is pinched just by resting the clamp in place. The P-type blade is half inch high or 12.7 mm, while the straight blade is 13 mm. I'm going to try to make this work for a range of blades, something like 12 to 13.5 mm. The key for this is milling this face a little bit more so that a step is left on the part. That step and the fact the screws are on the opposite side will make the clamp be a clamp. Yep, I don't think the blades will go anywhere. This big tab of metal. Although it could be completely removed, I'm going to keep it. I'm just going to make it shorter to align with the clamp. I think it will be helpful to keep the tool holder up on the bench. Chamfering all the edges on this face is just a matter of adding a shim as thick as the height of the step between the clamp and the body.
And chamfer away.
What I'm about to do next is a risky nice to have. I'm not sure if this is going to render this tool useless. Let's just hope not. This big chamfer on the front will allow for better visibility of the blade while it's cutting. I'm kind of concerned because it can actually weaken the tool, but I'll try to account for that. Now let's address the elephant in the workshop, the weird bandsaw cut. As you know, I had lots of problems parting off with this lathe. There was shatter, and worse than that, the tools were constantly digging in and crashing the lathe. What you're seeing here is me parting off a small piece of 1045. I did it, but took almost an hour. Very frustrating. In some clips like these, I actually saw my compound flexing, so I replaced it with a solid mount. That compound is now carefully stored. I didn't throw it away. And that change alone made things so much better. But there's something I saw on another YouTube channel that I couldn't resist trying. I mean, the spring part of tool holder from Winky's workshop. That made so much sense to me, to resolve the parting problems found on a small lathe like mine. Don't get me wrong, I'm a big fan of rigidity. But what if? And yeah, I know my tool holder looks very different, but functionally, it's just the same. I hope. So a big thanks to Winky for sharing this tool with all of us. And now you get why the back of the tool holder is partially split from the front. And also, why the same has to be done to the top, so it can actually flex. But a sharp split will be more prone to crack or break. That's why I will add a big radius to the flexing point. And here we go again.
Close your eyes and cover your ears.
Okay, I was hoping this wouldn't happen. And I don't have a slitting saw that's small enough to take this last bit without biting the wall of the hole on the other side. So I guess I'm left to cut this by hand. Finally, I'm able to break through, and I'm quick to jump into making the threaded hole for the height adjuster. I'm very close to the end and I want to try this so badly. But in order to do that, I need the knurled wheel that sets the height of the tool. So let's clean up this piece of 4140. I decided to go with 4140 because it resists better to rust, and that's what I want from this knurled surface. Knurling is a tedious process, at least for me anyway, and this time I'm preparing for the future. What I mean by that is that I'll be knurling a longer piece of stock than I actually need for this tool. That way I'll have a leftover piece that I can use later, if or when I need it. I think the knurling came out okay, but I've done better with mild steel. Also, this took more time as 4140 is a lot more harder to deform. Maybe a scissor type tool would have helped? I don't know. I didn't apply a lot of pressure on each pass because this bump type tool is not very good for the spindle bearings. Threading the end of a rod provides a good way to hold a part like this, otherwise we wouldn't have a good way to face it on both sides. Well, the knurling works. With the wheel finished, I'm going to add one last screw to the tool. This screw will act as a flexing limiter. Winky mentions this helps preventing the blade going under the knob at the end, that is, when parting off solid stock. I think it makes sense to have a way to adjust. Oh no. No. Come on. I was right at the end, and I mean right at the end. Okay, think. What are the options now? I could leave it like that and drill another hole. No. I could use a nut and weld it to the tap. That can leave some marks on the tool. Still no. Let's try something else. Okay, this will not work. I guess I need to drill it. This is an HSS tap with 5% cobalt, so I have to use carbide. I'm going to start with this 3mm end mill. This one should be good up to 65 Rockwell. I'm doing this very slowly. The last thing I want is to break the end mill in there. This doesn't feel right, but it might have been enough to create a flat spot for my spot drill. Let's try it again, very slowly. This thing feels hard, but the spot drill is cutting. I have 18mm to go, I just hope I don't break anything else. And if that wasn't hard enough, at the end the tip of the tap broke in small pieces that found their way into the slot. Removing them was a nightmare because they started to dig into the metal as soon as I tried to push them out. Eventually I managed to remove them, but what do you do with a 4mm hole now? Well, going up one size is kind of obvious, but I'm afraid I'll find some leftovers of the HSS tap in there. But I also don't want to go to M6, so let's try opening this up to 4.2 and see how that feels. Everything went well, M5 it is. And with that done, the only thing left to do is make this tool feel nicer and better looking. Here is the finished AXA tool holder. I think it looks pretty cool. So basically the blade is held on the front, which is partially split from the back. A second slot, parallel to the top, leaves only this portion right here connecting the front to the back, and that will allow for this whole part to flex. The blade is clamped with 4 screws from the bottom, and the way the clamping works guarantees the blade is always pushed upwards. That means the top of the blade should never sit sideways, because it registers against the tool holder. You can see that clearly in this shot. You can even see how the blade is correctly tapering down, both along the head and foot. Then we have the last screw we added to the tool, to control how much flexing should be allowed. And that's it! Enough with the talking, let's test it! Unbelievable! Let's try power feeding. Now I want a thin shim, let's say 0.5 millimeter. Pretty close, and looks like the tool is not digging into either side. This thing is totally a game changer for me. I want to try it more aggressively. Whoa, this just wants to cut. What a difference from before. Let's try faster, 500 RPM. Did you see how fast those chips were being ejected? That's just insane. I also tried 1045 and the tool cuts about the same, so next let's go straight to 4140. Wait, did you see that? That's a lot of flexing, but nothing looks broken, so let's continue. I think the problem is the blade. 4140 is harder and because of that requires more tool pressure to cut. Having a wide blade doesn't help. I'm going to change to the other one and we'll continue the cut. Much better now. The feedback of the tool is just excellent. It's really easy to control the cut. You know what? Let's see how much it flexes with the DTI. Goes between 0 and 1000, maybe 1.5. It's like it's self-adjusting and adapting to the cut. Or maybe that's just vibration. I don't know. Shall we try stainless? Stainless is not difficult if the tool is engaged and the feed is constant. Going slow and interrupting the cut, that's asking for trouble. The example of that is this shot with power feed. To be honest, I still feel kind of nervous parting stainless using power feed. You never know, things can go south all of a sudden and I think hand feeding is just safer. Having said that, let's increase the feed rate and see what the indicator tells us. For one, the tool definitely flexes more with stainless. I don't know if you noticed it, but there's a moment where it most certainly would crash if it was a rigid tool, but instead it readjusted and continued the cut. I think if I had to describe this tool with one word, that word would be forgiving. I've lost the count of the times this tool saved the lathe from crashing during the tests. But we're not done yet. I want to try this on aluminum. I guess there's not much to say about that. Cuts like a hot knife. I'm amazed with this whole transformation, both in the machine and in myself. Parting off was something that worried me every time I had to do it, and now I'm confident I'm able to do it. Of course, I'm not going to push it hard all the time. If I did it was just to show you what this is capable of. And I'm sure there's a lot of you with bigger lathes, and even with lathes like mine, that don't have any problems parting off stock. But I had. And now I have something that works. I will not bother trying to improve it any further, it just works. I think the solid tool post mount also plays a role in making this tool successful. Rigidity must exist in the right places to allow the flexing happening where and when it should. But you tell me why you think this works so well. Dare I say almost as good as a rear tool post?